Hi, pre-calculus students. We are working on section 11.6. We're going to talk about natural logarithms. All right, so our notes and vocabulary include this concept called natural logarithms. And basically, a natural logarithm is a logarithm that has base e as its base. So what it looks like is log base e of some number, let's say of x, right, is equal to y. So this would be a function that is the natural logarithm. But we don't ever see this written in that way. We generally write it like this. So when you see ln x, that really means log base e of x. And so the natural logarithm, it's called the natural logarithm because oftentimes in natural processes and things that occur in nature, we will see this as a way, we will use base e as a way to denote growth and decay. And so it is considered the natural logarithm when we think about the inverse of that process. And so speaking of inverses, we can talk about the anti-natural log, which is a little bit which is going to be a lot like what we talked about, just the anti-log in the last chapter or so, last section or so, where really we're really thinking about rearranging this logarithm. So if I have the natural log of x, we're considering the idea of taking the anti-log, meaning we're going to be thinking about e to a certain, let's say this is y, e to a certain power is equal to x. And so we're thinking about rearranging it so that we can figure out what the value is if we were to consider it as an exponential relationship. All right, and we'll see that soon. So let's take a look at this first example. It says, refer to the application above. I've copied it here. In a particular study, sociologists determined that the time t equals at time t equals 0, 5% of the people in a group have heard a certain rumor. After 2 days, 25% of the people in the group had heard that rumor. How long will it take for 80% to hear the rumor? Now, the information that we're given in the beginning of the chapter is that there's an equation that sociologists use in order to determine how long it would take for a rumor to spread amongst a population of people. So let's start here. Sociologists studying a group of people determined that the fraction of people in the group P who have heard a rumor after T days can be represented by this equation, where P sub 0 is equal to the fraction of people who have heard the rumor at time T equals 0, and K is a constant. So we need to do a little bit of calculating here in order to figure out what K is and see if we can calculate this value. The good thing is that we have two bits of information. We've got 0, 5%, and we have 2, 25%. What we're looking for is, what would this be if we had 80%? Let me make that percent up here look good, okay? So let's think about how we can do that. So looking at this equation, what I'm noticing is that we could find this out pretty easily if we knew exactly what K was. Let me highlight that, see if I can do it. If I can figure out what K is, and if I know what P sub 0 is. And we were given that P sub 0 is the fraction of people who have heard the rumor at time equals T equals 0. So this bit of information is going to help in that way. So P, let's just write it like this. P is equal to, and I'm going to put P is equal to, and so instead of putting 5% because we're talking about a fraction, I'm going to put 5 out of 100. And when I put 5 out of 100, what that really means is 0.05. Are you guys with me? Times e to the kt. This is my equation so far. Let's get rid of this. All of that is going to be over 1 minus 0.05 times 1 minus e to the kt. So this is the formula that we're starting off with using this bit of information. Still need to find k, and I'm going to do that using this bit of information. So I'm going to substitute in this information to see, because I already have an ordered pair that's other than this 0 ordered pair. I have an ordered pair that's going to work. So watch. So I'm going to put 25% over here. So I'll put that as 0.25. Let me make that a little darker. 0.25 is equal to 0.05 e to the kt power. Here, t is 2. So I'll put a 2k there. All of that will be over 1 minus 0.05 times 1 minus e to the kt, again, 2k power. So now this is kind of cool. What we need to do is basically solve for k, because then I'd have a full equation, and then I'd be able to find this information here. What time period would it take for 80% of the people to have heard the rumor? So how do I solve this? That's a great question. First thing I want to do is get this stuff out of the denominator. So I'm going to multiply both sides of the equation with this. All right, so once we've multiplied both sides by the denominator over here, this is what we get. Now we got to go through the weeds of dealing with it. So one thing I'm going to do is deal with what's in the brackets first by using the distributive property here. So I end up with 1 minus 0.05 and then plus 0.05 e to the 2k power. You guys with me? And then I can go ahead and multiply by my 0.25 over here. And then I have 0.25 times, now this is going to be 0.95, right? Plus 0.05 e to the 2k. This became a 29. I don't know how that happened. My bad. And then so we're going to further multiply this through. And when we do that, we get this 0.2375 plus 0.0125 e to the 2k is equal to 0.05 e to the 2k. And so now we still trying to get this whole thing together. We're looking for k. Remember, let's not forget that. So we're going to move everything over to one side. Not everything. We'll move the e term over to the other side. And so we'll get 0.2375 over here, and then we'll subtract this. So I have 0.05 e to the 2k, then I've got 0.0125 e to the 2k. And so when I subtract 0.0125 e to the 2k on both sides, we get 0.0375 e to the 2k. Let's go ahead and isolate our e value. So when I do that, I'm going to divide both sides by this value here. So 0.2375 divided by 0.0375 is what I'm going to get here. What I'll do at this point, after I deal with this sound, I'm not even feel like doing it, but what we need to do is figure out how to solve this. So we're going to take the natural log of both sides. So the natural log of this thing here, 0.2375 over 0.0375 is going to equal the natural log of e to the 2k. Remember, natural log of e to the 2k is really log base e of e to the 2k, right? And so this is saying e to what power is going to give me e to the 2k? E to what power gives me e to the 2k? Taking the natural log annihilates the e, so I'm just dealing with 2k. Because think about it, e to what power gives me e to the 2k? 2k, right? So then when I take the natural log of both sides, I get 2k over here. Almost done. I really want to solve for k, so I'm going to divide both sides by 2. Let me move this equal sign down so it doesn't look crazy. All right, so this is what I'm focused on. I took the natural log of this side, the natural log of this side. When I took the natural log of this side, I had ln point blah, 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 blah. When I took the natural log of this side, the e I got rid of the e and I was left with 2k. Finally, I'm going to divide both sides by 2, so my answer will be k. What is k, you ask? So K is 0.9229. So we've been through a lot. What were we fighting for? I know you've forgotten. So have I. Let's go back up to the problem. So we were given some information and we want to figure out how long it's going to take for 80% of the population to know about this rumor. And now we needed to find that K value. So now we're going to, I should shrink this. We're going to go right back up to the original equation. And what we're going to do is, let's go ahead and see if we can get some of this out of the way. I know I'm making it look bad. Stay with me, friends. So we're going to get some of this stuff out of the way, and we're going to use the information that we got so we can use that original equation to solve the problem. Isn't this going to be fun? It's going to be fabulous. Okay, so let's go back. So our original equation had P, which in this case now, let's use a different color. Maybe that'll help. P, which is going to be that ratio, so it's going to be 80%, so it's going to be 0.8. That makes sense? Is equal to P sub 0, which is still 0.05, e to the k. Remember what e is? Not what we know what e is. Remember what k is? It's going to be 0.9229. I'm trying to use my memory here. Was it that? Yeah, it is. 0.9229 times t, because we're looking for that time. All of that over 1 minus 0.05 times 1 minus e to the 0.9229t, close parentheses. So now we got to solve for t. How are you feeling right now? I'm feeling the same way. What? Okay, so what we need to do is go back through all the cool things that we did before, and this time instead of solving for k, we're going to solve for t, because last time we had t is 2, but now we're looking for k. We're looking for t. We already got k. So this is going to be fun. We're going to multiply both sides by this. Let's see what we get when we do that. So this, when we multiply the denominator on both sides, this is what our equation will look like with a little bit of distributive property and simplification. We get this equation here, and then of course we're going to do just like we did last time, which is to move this over to the other side. So when I move this over to the other side, it's going to give me, I'm going to be subtracting this from this. I'm going to get 0.01 e to the 0.9229t. And just like last time, we're going to isolate the e term by dividing both sides by this coefficient. So we're going to get 0.76 divided by 0.01, which is actually going to be 1, 2. It's going to be 76 is equal to e to this business here. And so now what we're going to do is take the natural log of both sides. So the natural log of 76 is equal to the natural log of this, which we know basically undoes the e. It's kind of like the anti-e power. So we end up with 0.9229 over here times t. What we're going to do now is isolate that t by dividing both sides by 0.9229. So the natural log of 76, this is now we got to get our calculators. We're going to do that. And our calculator tells us that t is equal to approximately 4.7, and that 4.7 refers to the days that it would take for a rumor to spread to 80% of a particular population. Fun! Let's go ahead and look at the next problem. So one of the things we need to be able to do is remember that we can use the change of base formula in order to change things to make it more convenient. So in addition to using the common log, when we have something like this, we can use the natural logarithm to evaluate it. So basically, you remember the change of base formula says if you take the log of this base b and then divide it by the log of this base b, you'll get the answer. So I know that log base 6 of 254 is equal to the natural log of 254 divided by the natural log of 6. And I'm going to just put that in my calculator. And I get approximately 3.0294. We get approximately 3.0904. Example 3 gives us an opportunity to solve this situation. So if we know that the 6.5 is equal to negative 16.25 times the natural log of x, and we want to solve for x, we'll first divide both sides by the negative 16.25. And after we do that, we'll be left with the fact that 6.5 divided by negative 16.25 is equal to the natural log of x. Let's remember what this means. Natural log of x really does mean log base e of x. So this says that if I want to solve for x, and I'm going to look at this as an exponential relationship, what I'm going to do is say e to this power here is equal to x. Are y'all with me? So e to the 6.5 over 16.25 negative is equal to x. And I'm just going to shove that right into my calculator and tell you that the answer is 67 hundredths. An example 4, we're going to solve each equation or inequality by using natural logarithms. Let's remember that if we have two things that are equal, we can take the natural log of both sides and that equality will be maintained. So I can take the natural log of 3 to the 2x and know that that is equal to the natural log of 7 to the x minus 1. From our log laws, we know that we can rewrite this side, this left side of the equation, as 2x times the natural log of 3. And then similarly on this side, I will write x minus 1 times the natural log of 7. So let's put a 1 there. So what I do here, because I need to get the x terms all to one side, this x term in the parentheses isn't quite free. I need to free it by using the distributive property here. So I'm going to distribute through. So first 2x times the natural log of 3 is equal to the natural log, or x times the natural log of 7 minus the natural log of 7. Do you see how we did that little distributive property? Because the natural log of 7 is a number. The next thing I want to do is move my x terms over to one side of the equation. So this is an x term and this is an x term. So I've got 2x times the natural log of 3 minus x times the natural log of 7 is equal to negative the natural log of 7. Stay with me. To get x by itself, I'm going to factor the x out. So I've got x times 2 times the natural log of 3 minus the natural log of 7 is equal to negative the natural log of 7. Now I'm going to divide both sides by this expression here. So then I get that x is equal to negative the natural log of 7, all of that over 2 times the natural log of 3 minus the natural log of 7. Take a moment to take that in. Whew. Now what we get after we calculate this using our calculator, of course, is that x is equal to negative 7.7433. Let's take a look at this situation. Here we have an inequality. And so just like with the equation, we know that we can still take the natural log of both sides. So let us do so. If I take the natural log of 6x squared minus 2, it'll still be less than the natural log of 48. So when I use my relationship here, I know that x squared minus 2 times the natural log of 6 will be less than the natural log of 48. And so we know that we need to solve for x. So I'm going to divide both sides by the natural log of 6. When I do that, this is what I get. And since the natural log of 6 is a positive number, we're sure we don't have the sign flipping or anything like that. Now we're going to isolate that by saying that x squared, we're going to add 2 to both sides, is less than the natural log of 48 divided by the natural log of 6 plus 2. And then finally, we need to take the square root. X has to be less than the square root of the natural log of 48 over the natural log of 6 plus 2. And with a little bit of calculator action, I would get that x is less than 2.0397. But now when I'm thinking about it, this is not how we take care of quadratic inequalities. And that's really what this is. And so if you remember, when we deal with quadratic inequalities, what we need to do is really consider what exactly will make this situation 0. So what am I talking about? Well, if I simplify this, if I just deal with that, I'm going to come over here. I'd have x squared is less than, I think, approximately 4.1606. And so what we would do is anytime we have something like this, we would set it equal to 0 or compare it to 0, really. So now what we have is this inequality. X squared minus 4.1606 is less than 0. So the question is, when is this situation less than 0? What does this look like? So if you were to remember, a couple ways of looking at this. If you were to remember, this is kind of like we could look at it as a difference of squares. X squared, I know this isn't a perfect square, but just rock with me. So if we thought about factoring this, it would be x minus the square root of 4.1606. That would be one value. And then x plus the square root of 4.1606. Hope this is ringing a bell. And that's less than 0. So when is it less than 0? When can we have that value work out in that way? Well, first of all, the square root of that is going to be this. So this is really x minus 2.03. Let's just do 2.04. X minus 2.04 is one factor, and x plus 2.04 is the other factor. So the question is, when is this thing equal to 0? Well, it's going to be equal to 0 when x is equal to 2.04, but we don't want it to be equal to 0. We only want the values where x is where this entire expression is less than 0, not equal to 0. So here's what we're going to do. We could use a graphing calculator for this too, but we're going to just use this. We know that the two 0 places would be negative 2.04 and positive 2.04, right? So I'm going to put open circles here. We don't want those answers. But what happens here if we were less than negative 2.04? Let's say at negative 3. So at negative 3, this part of the expression would be negative, and at negative 3, this part of the expression would also be negative. So we'd have negative times negative, which is a positive. So everything below negative 2.04 is going to be positive. And so let's check what's going on in the middle. If I put a 0 here, I'm going to get a negative answer. A 0 here, I'm going to get a positive answer. And I know that negative times a positive will be a negative. So my answers from this interval from negative 2.04 to 2.04 will be negative. And finally, if I choose a number like positive 3, plug it in here, I'm going to get a positive answer here and a positive answer here, and therefore this whole section is going to be positive. So let me make it very plain. Positive values will come when we are dealing with values that are below negative 2.04 or above positive 2.04. Negative answers will arrive when we're dealing with values that are just between negative 2.04 and positive 2.04. What does this have to do with the problem? Well, let's remember, we want answers that are going to make this thing less than 0, and that's only going to occur in this interval here. So our answer is negative 2.04, really that number, but negative 2.04 to 2.04, not including those two endpoints. Or of course, we can write it as x can be any value between these two numbers. Are you guys with me? I hope so. I feel like that problem it seemed simple and then it became a little bit more dramatic. So I honestly think that that was pretty good. If it made sense to you, that's good. If not, we definitely should talk about it. And other than that, that's all I have to say about section 11.6. Guys, take care. I look forward to talking to you soon. Bye-bye.